Hello and welcome. My name is Ashish Ahuja. I'm an applications engineer with Texas Instruments. Today we will talk about the floating point unit on the state-of-art new Tiva 4C123X family of microcontrollers. By the end of this presentation, you will be familiar with the IEEE 754 standard of representing floating point numbers, the floating point unit on the TM4C123X microcontrollers, its modes of operation and registers, CMSIS DSP library, and TivaWare for C-series APIs. We will also talk about some points you should keep in mind while using the floating point unit and also point you to resources where you can find information and learn more details. All this knowledge will equip you with the resources that will serve as a great starting point to begin developing your applications using floating point unit. So let's get started. Floating point is a method of representing real numbers on computers. Floating point representation is similar to the scientific notation of representing numbers. Representing numbers using floating point provides a way to support a wide range of values as compared to fixed point representation using the same number of bits. Each number has an exponent and a fraction. There are several IEEE formats to represent floating point numbers such as half precision, single precision, double precision, and quadruple precision. Let us take a closer look at the IEEE 754 standard to represent floating point numbers in single precision format. In this format, a real number is encoded using 32 bits, out of which 23 bits are used to represent the fraction, 8 bits are used to represent exponent, and the remaining 1 bit is used to represent the sign. The expression to determine the decimal value of number knowing its fraction, exponent, and sign bit is shown on the screen. Let us quickly look at an example to familiarize ourselves with this concept. A 32-bit number is represented on the screen in which the lower 23 bits are used for fraction, the next 8 bits are used for exponent, and the most significant bit is used for sign. The new Cortex M4 core has a IEEE 754 compliant single precision floating point unit with single instruction and multiple data for 16-bit data types along with a 32-32 multiply accumulate with 64 result. The processor delivers exceptional power efficiency through an efficient instruction set, thanks to its extensively optimized design. Floating point core supports hardware division, multiplication, addition, etc. Although it cannot replace a DSP, it can be used in simple signal processing applications using the DSP-like instruction set. Higher precision in control loops, faster signal processing, lower latency, and easier integration with tools such as MATLAB and LabVIEW are some of the advantages of using TM4C123X family of microcontrollers. The Cortex M4F floating point instruction set does not support all operations defined in IEEE 754/2008 standard. Unsupported operations include, but are not limited to, the following: remainder, round floating point number to integer valued floating point number, binary to decimal conversion, decimal to binary conversions, direct comparison of single precision and double precision values. The Cortex M4 floating point unit supports fused MAC operations as described in the IEEE standard. For complete implementation of IEEE 754/2008 standard, floating point functionality must be augmented with library functions. Embedded processing applications that involve data compression, sensor array processing, measuring and filtering signals can benefit from floating point unit. TM4C123X microcontrollers can be used in control systems such as solar inverters, motor control, and lighting control, etc. Alternatively, digital control applications that demand an efficient, easy-to-use blend of control and signal processing capabilities can also utilize the floating point unit for embedded processing. The new floating point unit supports conversions between fixed point and floating point data formats and floating point constant instructions. It supports 32-bit instructions for single precision data processing operations and has decoupled 3-stage pipeline. There is a hardware support for denormals and all IEEE rounding modes. The floating point unit also supports saturation math. In order to conserve power, the floating point can be disabled when it is not required. Now, let us take a brief look at the instruction set of various Cortex M cores. Several new instructions have been added to Cortex M4 in addition to the instructions which were already supported in Cortex M3. Cortex M4F is ISA compatible with Cortex M4 and M3 instructions. Now we are going to pause for a few seconds so that you can view the instruction set. The floating point unit can be operated in three modes: full compliance mode, flush to zero mode, and default NaN mode. In full compliance mode, the floating point unit processes all operations according to IEEE 754 standard. In flush to zero mode, the floating point unit replaces a tiny result where the destination precision is smaller in magnitude than the minimum normal value before rounding with a zero. This mode can be enabled by setting the FZ bit in the floating point status control register. In default NaN mode, the floating point unit returns a default NaN when the result of any arithmetic data processing operation that involves an input NaN or that generates a NaN result. This mode can be enabled by setting DN bit in the floating point status control register. The floating point unit provides an extension register file containing 32 single precision registers. There are 16 64-bit double word registers D0 through D15, 32 32-bit single word registers S0 through S31. Compilers can use floating point registers for floating point or non-floating point code. Please note that only single precision floating point is supported except for only two double precision load and store instructions. Okay, so let us take a closer look at some of the instructions in the floating point unit of Cortex M4. There are about 36 instructions in the instruction set of the floating point unit, such as absolute value, addition, comparison, division, multiplication, etc. of floating point operands. Please note the table shown on the screen does not include all instructions. Please refer to the ARM Cortex M4 Technical Reference Manual for the complete instruction set. Also note, in some documents you may find floating point instructions beginning with the letter F instead of letter V. Such instructions are equivalent. For example, fadd.f32 is equivalent to vadd.f32. In order to provide a single standard across all Cortex-M based processors and to enable code reuse across various software projects, ARM has come up with a vendor-independent hardware abstraction layer called CMSIS, Cortex Microcontroller Software Interface Standard. In addition to other components, CMSIS consists of a DSP library which contains over 60 functions in both fixed point and single precision floating point implementation. This makes it really easy for a user to utilize the capabilities of floating point unit. CMSIS DSP library includes separate functions for operating on 8-bit, 16-bit, 32-bit integer and 32-bit floating point values. It has been developed and tested with MDK ARM and can also be compiled on various tool chains such as TI's Code Composer Studio. Additionally, CMSIS DSP library supports single public header file for Cortex M4, M3, M0 with little endian and big endian. The CMSIS DSP library is divided into a number of modules such as basic math functions, fast math functions, filters, transforms, matrix and interpolation functions, each covering a specific category of function calls. The CMSIS DSP library can also be recompiled on TI's Code Composer Studio. The library has separate functions for performing operations on 8-bit integers, 16-bit integers, 32-bit integer, and 32-bit floating point values. Some of those functions are shown on the screen. Let us pause here for a few seconds and read through the list of functions. For details on function descriptions, return type, arguments, and examples, please refer to the CMSIS DSP library documentation made available by ARM. The CMSIS DSP library is completely written in C, builds and runs on the Cortex M4, M3, and Cortex M0 processors. Maximum use of Cortex M4F intrinsics allows for high performance in Cortex M4 based devices. DSP library performs about 2 times faster on Cortex M4 in comparison with Cortex M3. It also performs about 10 times faster on Cortex M4 with floating point in comparison with Cortex M3. The diagram on the screen shows a quick comparison between the CMSIS DSP library performance on Cortex M4 and M3 platforms for different operations. For example, using DSP library on Cortex M4 with fixed point consumes 70% less CPU cycles as compared to Cortex M3 for matrix multiplication operation. Likewise, using DSP library on Cortex M4 with floating point consumes 91% less CPU clock cycles in comparison with Cortex M3 for correlation operation. CMSIS DSP library also contains several examples to demonstrate the use of DSP library functions. It can be downloaded from ARM's website and comes with examples and documentation. These examples can be built using TI's Code Composer Studio, which can be downloaded from ti.com/ccs. In order for use with CMSIS DSP library and the examples with TI's Code Composer Studio, you will have to first build a library on CCS. We have an application note for you that describes the process required to build the DSP library in Code Composer Studio version 5. The application note also describes how to use CCS v5 to build, run, and verify the ARM DSP example projects that are included in the CMSIS package. This application note and several others are available on the TI website. Please go to ti.com/tiva-c and click on the Technical Docs tab. Please bookmark this link for your convenience. Now let's spend a minute and take a look at the software that comes with the TM4C 12X family of microcontrollers. TivaWare for C series is an extensive suite of software designed to simplify and speed up embedded application development using the Tiva C series microcontrollers. TivaWare for C series includes Peripheral driver library, graphics library, USB library, and sensor library, which include several APIs to configure and initialize different peripherals of the Tiva C series microcontrollers. These libraries come with the source code, which is mostly in C. They are pre-compiled for use as is and can also be adapted as desired. TivaWare for C series also includes bootloader, several code examples, and third-party packages that allow you to focus on your application development and not so much on how to set up the microcontroller. The Peripheral driver library in TivaWare for C series includes a set of function calls, commonly known as APIs, which can be used to initialize and configure floating point unit without having to know too much about various registers and bit configuration. More details about the functions, including the description, prototypes, arguments, etc., can be found in the driver lib documentation, which is available in the docs directory of the TivaWare for C series. I strongly encourage you to take a look at that before you start using these functions. As I mentioned previously, TivaWare for C series also comes with a sensor library that allows you to develop exciting embedded applications using different types of sensors with TM4C 123X family of microcontrollers. Sensor library is organized in 3 layers: transport, sensor, and processing layers, and it provides a set of drivers and API functions to initialize and configure a variety of sensors to measure temperature, pressure, acceleration, magnetism, and physical orientation. Sensor library benefits from the floating point capabilities of TM4C123X microcontrollers to process the raw data captured from various sensors and presents it to the user in standard international units, enabling them to process the data with greater convenience and simplicity. Some example APIs are shown on the screen. In order to make it easier for you to add sensor capability for your embedded applications, we have developed SensorHub Booster Pack, which consists of onboard gyroscope, accelerometer, and compass for motion sensing and tracking, pressure, humidity, temperature, and light sensors for environmental monitoring. When used with the Tiva C-Series Launchpad Evaluation Kit, it serves as a great starting point to jumpstart embedded application development using different sensors using Sensor Library and the TM4C123X microcontrollers. You can pick and choose from several IDEs such as TI's Code Composer Studio, Kyle's Microvision, IAR's Embedded Workbench, and Mentor Embedded's Sorcery Codebench. We have also included several examples that demonstrate how you can streamline development of sensor-enabled embedded applications and add sense to your projects. We have an extensive repository of excellent documentation, including device data sheets, user manuals, application notes, etc., that have been created to strengthen your understanding about TM4C123X devices and accelerate design and development of your project. If you have a technical question, you can contact Tiva C-Series experts on the TI E2E forum. Please visit ti.com/tiva-c for technical documents, ordering samples, downloading tools and software, and e2e.ti.com to obtain technical guidance. So today, we learned about the floating point unit in the state-of-art new Tiva C-Series TM4C123X family of microcontrollers. We began our discussion by learning about IEEE 754 standard for representing floating point numbers. That led us to a discussion on functional description of the floating point unit on the TM4C123X microcontrollers, its modes of operation and registers. In the end, we walked through SimSys DSP library and TivaWare for C-Series, a software that enables you to jumpstart embedded application development with TM4C123X devices. We also looked at various APIs which can be used to initialize and configure the floating point unit on TM4C123X family of microcontrollers. Good luck with your first floating point project. Stay tuned and have fun with TM4C123X devices.